Okay, welcome back, everyone. I just wanted to do a quick video explaining why we represent space for 3 dimensions with a 2-dimensional shape. And I thought we just kind of walk through 1D, 2D, and then finish on 3D. This is just sort of a response to the Joel Speranza video you guys watched earlier, which had geometric interpretations of my 3D planes interacting. I thought a question that some of you might have is, why are we using planes to represent a 3-dimensional object? I'm going to try to help answer that question a little bit in this video. So maybe I might get you guys to watch this before you watch the Joel Speranza videos, but really all we're trying to get out here is how we could picture these geometric representations of our matrices. Again, the main takeaway we need to have is being able to use Gaussian elimination to solve my systems of equations. However, we do require some knowledge of what this looks like geometrically. So hopefully this video can just shed a bit of insight into how we sketch in 3 dimensions and why we represent that with a plane. So let's just start with 1 dimension. Now, if I have a 1D plane, if I represent an equation, well, if this is like an x-axis, I really only have options of like x equals 1, 2, 3, or 4. So if I have a 1-dimensional space, I represent this with just like a little dot. I put a little dot over 1 here. That's all we could really do. This is kind of like our intro to sketching. So if I was to plot x equals 1 on a number line, all I do is I take my little dot and I put a little dot here. This is sort of like our introduction to sketching. If I come down to my 2D space, well, that's going to be an equation like y equals x plus 1. Now, well, y equals x plus 1, we can use a straight line to represent this, where I have a relationship between x and y. So I kind of have like a rule. If I put 1 in for x, I get 2, put 0 in for x, I get 1, etc., etc. And I can form this line here, which is y equals x plus 1. Okay, now let's go on to 3D. And hopefully now we can start to see maybe there's a bit of a pattern forming in our minds. 1D sketching is a dot. A dot we say is 0 dimensions, really. For 2-dimensional sketching, we have a 1D sketch. We use a straight line. So for 3-dimensional sketching, we can represent this with a 2-dimensional sketch, or like a sheet of paper or a plane. Just note, we can also represent this with some form of straight line moving in 3-dimensional space, which can be a hard thing to kind of picture. We'll look at that more when we do vectors. So with vectors, we'll look at 3D vectors, and we'll do more work on that. For now, it's just trying to get an idea of, hey, why can we use like a sheet of paper, or why can we use a 2D plane when we're talking about the geometric interpretation of our matrices? So first, because this will be the first time for a lot of us who've ever seen 3-dimensional axes, let's just have a look at what my axis represents. It's a little bit different. You can see my x-axis is actually the one that's coming in and out of the page, and my y-axis is over here, with my z now being my vertical. Now, this is quite common practice. It makes it a little bit easier to kind of picture or draw out our sketches. I'm going to give an example with a point, then we'll look at doing it with a full line. Let's just do a point, and we can see, how can I put a point onto a graph like this? So let's just look at the point of 2, 1, 1. So let's just keep it nice and straightforward. With my point here, I still have an x, y coordinate system here. So I still have 2, 1. And let's put 2, 1 on my 3-dimensional space, or on these. And let's put 2, 1 on my 2D axes, and then I'm going to project my 3rd dimension on top of that. So if I come out 2 along my x-axis, again, my x-axis being the one coming out of the page, well, I come across 1, I come across 2 units like so. Now I come across 1 on my y-axis. Let's just put the 1 somewhere along there. If I draw some little broken lines parallel to my axes, if I start at the 2, so I'm going to come out here to my 2, I'm now going to move 1 unit parallel to this line here. I will now want to move 1 unit parallel to this line here. So that's going to be 1 unit across like so. So I'm going to have a dot. If I come down here, you can see I get a dot somewhere around here if I was representing this in a 2-dimensional space. Now, that 2-dimensional space is technically kind of sitting out of the page, but again, we only have 2 dimensions to sketch in, so it'll always be a little bit hard to wrap our heads around where this sits. I now want to project my 3rd dimension. So my 3rd dimension now is going to be up here. I'm going to go 1 unit up this way. So now I'm going to come 1 unit parallel, and that's going to give me a dot something like this. So that's one dimension that's sitting 1 unit above these two axes here, which can be a little bit hard to picture, but that is what I have happening here. One thing I've done, which can kind of help me picture how this works as is 3 dimensions, is I can kind of mix my order up with how I kind of plot my points. So instead of coming down 2, then across 1, I could instead come across 1 and then down 2, like I've done here, to this point. Then I can move up 1. If I go up 1 first, well, I can come up 1 this way. I go across 1 out to here. Then I could come down 2 to this point. And if I kind of keep doing this, if I start from this point here, I go up 1 first, then I come across here. What I end up creating incidentally is almost like you can see I've got like a box. I've almost created a box. And we know boxes exist in 3-dimensional space. You don't need all these dotted lines when you plot our point. I just wanted to help kind of you guys to picture that this is sitting in a 3-dimensional plane. So that's it for a dot. Again, we'll look more at this when we do vectors, but I felt like we need to have some idea of what's happening. Let's just start with a point, and then we'll expand out to looking at what happens with a line. Okay, let's say now I wanted to sketch the line of 3x plus 2y plus z equals 7. I now have an equation of a line in 3-dimensional space. And this is still a linear equation. Everything here is power of 1. So normally we'd represent this with some form of straight line if it's a 2D shape. But this time we're in 3-dimensional space. So our linear equations in 3-dimensional space will be a 2D object or a plane, and we'll kind of see why. So the way I actually solve this is with a very familiar skill. If I have 2D space here, well, if I want to find my x-intercept and my y-intercept, I'd find this number here by letting y equals 0. I'd find this number here by letting x equals 0. I'm going to do the exact same thing, except I'm going to let both x and y equals 0, y and z equals 0, x and z equals 0. So let's just start by finding our y-intercept. So to find our y-intercept for a 3D equation, that is going to be when x equals 0 and when z equals 0. So if I go ahead and do that, that is going to give 0 plus 2y plus 0. I guess I should write 2 times 0. Is equal to 7. So that means that y is going to equal 7 over 2. To find my x-intercept, that is going to be when y equals 0 and when z equals 0. So that is going to become 3x plus 2 times 0. Sorry, I should have put a 3 here. It doesn't change our answer. I just copied the number down wrong. So it's 3x plus 2 times 0 plus 0 equals 7. So x equals 7 over 3. And the final one, to find my z-intercept, that's kind of the new part that we haven't done before. Well, that's when both y equals 0 and when x equals 0. That is going to be 3 times 0 plus 2 times 0 plus z equals 7. So that means that z simply just equals 7 in this case. So I've got my 3 intercepts. I'm now going to put these on my graph. Well, that's going to be for x, it's about 2 1/3. Let's just put that dot somewhere around here. For y, that's going to be 3 1/2. Let's put that somewhere around here, a little bit further along. And z is going to be 7, which I've realized I've made a very bad scale here. Let's just try to extend this line slightly. And we'll put my dot, let's just put our dot somewhere around here. And we'll re-put our z label back. So these are kind of my 3 intercepts. Well, that means I have an equation that passes through all 3 of those points. If I did this as a line, you can see I've kind of created myself here like a triangle of sorts that exists in 3-dimensional space. This here is going to represent a plane or a 2D object. Now, that's just the intercepts. It's going to kind of keep going this way. You can imagine it keeps going this way, it keeps going this way. So what I actually do wind up with is like a sheet of paper. So to look more like this, if I did the full version of what I have. But normally when we're doing these sketches, I just look at the intercepts because it's very hard to do the rest. So if I was just sketching based on my intercepts, I essentially would create a 2-dimensional triangle or a plane. Again, a sheet of paper is a better way to think of it, but this is why when I have a 3-dimensional diagram, I'm not talking about the intersection between 2 lines. I'm talking about the intersection between 2 planes or 3 planes. If we come over here, we can see I have the different intersections from planes. There's going to be a whole video we're going to watch after this. I've just decided now we're going to watch the video now by Joel on him kind of showing the different intersections between the planes. Because he's done quite a good job and he's put a lot of effort into making the sheets of paper. So why reinvent the wheel there? So you guys can watch that video. Hopefully that'll make a bit of sense. Again, the key takeaway, Gaussian elimination, finding solutions. We just need some understanding of, with the different solutions I get from my Gaussian elimination, I need some understanding of what that means geometrically. Are they intersecting? Are they the same plane? Do they intersect at a point? Or do they have a full line in common? All these different considerations.